Hello everyone, welcome to the third and final part of problems based on type of container. We are gonna talk about connected containers. We have already talked about closed and open container. So here I have drawn two containers and connected them by a valve. Here container 1 has a volume V1, temperature T1 and consists of gas A with moles Na. Similarly, the container 2 has volume V2, temperature T2 and consists of gas B. When the valve is opened, the transfer of gases takes place from one container to the another container, right? So these will move from one place to another until the state of equilibrium is established. Okay, so when valve is removed, they will move from one to another container until equilibrium is achieved. And at equilibrium, we will write the pressure of gas A in left part should be equal to pressure of gas A in right part. Similarly, the pressure of gas B in the left part or left container should be equal to pressure of gas B in the right container. So here gas A will move from left to right, gas B will move from right to left. So both of these gases will be present in the left as well as right container. So here we will have PA as well as PB. Similarly, here we have PA as well as PB. P represent the pressure here. Okay. So going further into the details of connected containers, we have gases A and B here, and when the valve is removed, we will be talking about that condition when equilibrium will be established. So you know volume and temperature conditions. And in the left container, we have moles of A as X moles, moles of B as Y moles when the valve is removed. Similarly, on the right side, what will happen? Moles of A will be total moles minus X, right? Na minus X moles because X have moved from one side to another. Similarly, B will have Nb minus Y moles, right? So this will be situation when the valve is removed, and we'll write at equilibrium the pressure of gas present in the left container should be equal to the pressure of gas A present on the right container, right? So pressure is nRT by V, we'll put these values. So here what's N is X, which is moles, multiplied by R multiplied by temperature in the left container T1 divided by V1 should be equal to how many moles are on the right side for gas A? It is Na minus X, right? Multiplied by R multiplied by T2 divided by V2. So this will be our first equation. Similarly, we will write the pressure for gas B present on the left side should be equal to pressure of gas B present on the right side. So putting values, it will be moles, which is Y R T1 divided by V1 should be equal to Nb minus Y. Here it is Y. Sorry, I have written X. It's Y. Basically, Y is the moles that has been displaced. So it will be Nb minus Y that will be left. So Nb minus Y multiplied by R multiplied by T2 divided by V2. So these are the two equations. So from these two equations, from 1 and 2, we'll obtain the values of X and Y, basically how many moles have been displaced after the valve has been removed. So we'll solve a problem here. Initial condition has been given. We have S2 and O2 on left and right side respectively in container 1 and 2. The volume has been given on both the containers. Okay, here the valve is present. When the valve is opened and equilibrium is attained, find out moles of O2 in smaller container, pressure of gas S2 and O2, find total pressure in each container. So we'll solve it here. So first we'll be drawing the diagram of the condition at equilibrium. So here we have two containers on left and right side. Let's name them 1 and 2. Okay, so we have S2 gas, which is 1 mole on the left side. So at equilibrium it will be left as X moles, and O2 that will come on the left side will be Y moles, and on the right side, to balance the total moles, we'll write for S2 it will be 1 minus X, total minus how much has been displaced. Similarly for O2 it will be total minus how much it is displaced. So 4 minus Y. These are moles basically on the right side or container number 2. Okay, and we have been provided with the volume as well as temperature. We'll write pressure of gas A on the left side should be equal to pressure of gas A on the right side. Here A is S2 basically and B will be O2. So what is pressure of S2 on the left side? So it is an RT by V, which is X multiplied by R multiplied by 300 divided by V1, which is 8.21, is equal to moles of S2 on the right side, which is 1 minus x multiplied by R multiplied by T2, which is 300 divided by what is the volume V2 here, 2 multiplied by 8.21. Note that temperature is same, so it will be cancelled out, R will be cancelled out, and we'll simply get the value of x, which is 1 by 3 moles. Okay, so we'll solve for y as well. So we had to find out moles of O2 in a smaller container, right? So which means we'll solve for y as well. So pressure of gas B on the right side should be equal to pressure of gas B on the left side. So for O2 we have y multiplied by R multiplied by T1, which was 300, divided by V1, which was 8.21, is equal to 4 minus y multiplied by R multiplied by 300 divided by 2 multiplied by 8.21. So we'll solve and get the value of y. It will come out to be 4 by 3 moles. We had to find out the value of moles of O2 in a smaller container. Which is a smaller container? It is left one. So we have got the moles, which is 4 by 3. Now we'll solve the second part. We have to find out pressure of S2 and O2. Note that we can take any container to solve this problem. Let's take the left one. So moles of S2 multiplied by R multiplied by T divided by V. So moles of S2 in the left container is 1 by 3 multiplied by 0.0821 multiplied by temperature in left container, which is 300, divided by volume in left container, which is 8.21. On solving, we'll get the pressure of S2, which is 1 atm. Similarly for O2, let's take the left container, moles of O2 multiplied by R multiplied by T divided by V. Let's just quickly put the value, which is y. What is the value of y? It is 4 by 3 multiplied by 0.0821 multiplied by temperature in the left container, 300, divided by 8.21. We'll get the value, which is 4 atm. So you can verify this answer by solving it for the right side as well, which means container 2. Okay, so let's quickly verify this. So pressure of S2 on the right side, it will be 1 minus x multiplied by RT divided by V. Okay, so basically RT2 divided by V2. So 1 minus, what is the value of x? It is 1 by 3, 1 minus 1 by 3 multiplied by 0.0821. What is temperature in the right container? 300, divided by volume in the right container. It is 2 multiplied by 8.21. So on solving, we'll get it 1 atm. Okay, so we can verify this. Similarly, we can solve for O2 gas as well. So pressure of O2 gas on the right side will be 4 minus y multiplied by RT2 divided by V2. So 4 minus, what is y? It is 4 by 3, and it will be 12 minus 4, it is 8 by 3. It will be cancelled out. It will come out to be 8 by 3 multiplied by 3 divided by 2. So it is 4 atm basically. So we can verify our answer. Now we'll solve the third part, where we have to find total pressure in each container. We can solve for any one container. Let's take the left container. So total pressure will be in each container, right? So it will be same for left as well as right container. So total pressure is pressure of S2 gas plus pressure of O2 gas. So it will be 1 plus 4. It will come out to be 5 atm. So this is our answer. So we have solved all the three parts here, right? So now we'll write an important note. If temperature is same in both the containers, then we can directly use this equation, which is final pressure multiplied by final volume is equal to final moles multiplied by RT. Since temperature is same, you can verify by solving the previous problem. Now moving on, here is an interesting problem. We have gas in left container, whereas right container is empty. The condition is given for volume and temperature. When the valve is removed and equilibrium is attained, find out moles of gas in larger container, which is right one. Okay, and find out the final pressure. So let's solve it. We'll draw the diagram of the condition at equilibrium. So we'll write at equilibrium, we have these containers on the left and right side, container 1 and 2. These are connected, and in between there is the valve which has been removed. And after removal of the valve, we'll have the gas present on both the containers. Okay, so the empty container will also have this gas, and on the left side the moles of gas that will be present there will be x moles. On the right side it will be 1 minus x moles. Okay, and we'll write the condition of volume and temperature provided to us, that is 10 liter 300 Kelvin and 40 liter 600 Kelvin respectively. Now we'll write at equilibrium. You know that pressure of gas on the left side should be equal to pressure of gas on the right side, right? So P is nRT by V, putting the values. What is the moles here? X multiplied by R multiplied by T, which is 300, divided by V 10 is equal to 1 minus X multiplied by R multiplied by the temperature here, which is 600, divided by 40. So here we'll solve and get the value of X. It will come out to be 1 by 3 moles. Okay, so we have to find out moles in the larger container. So moles of gas in container number 2 or larger container, it will be 1 minus X moles. This is the larger container because its volume is larger. So 1 minus X, it will be 1 minus 1 by 3. So it will come out to be 2 by 3 moles. So this will be our answer to the first problem. Now solving the second problem, we have to find the final pressure. So final pressure will be PF. So PF will be nRT divided by V. So we'll take any of these containers. Let's take the left one. You can verify for the right one as well. So its moles is 1 by 3, which is X, multiplied by R, which is 0.0821, multiplied by temperature, which is 300, divided by volume, which is 10. And on solving, we'll get the final pressure, which is 0.818 atmosphere.